Now we're going to talk about engine performance metrics, which use some of the results that I've just provided, and then an introduction to 3D flow modeling, which will form the basis of what I'll be talking about from tomorrow onwards. Okay, so let's talk about performance. Remember I spoke about the ideal cycle. Well, here it is in a PV diagram where I'm plotting the compression stroke as a straight line and a log plot here. There's a log scale of pressure against log volume. Slope here would be related to the ratio of specific heats, as we've seen. Then I have constant volume combustion, and then I have expansion, again, an isentropic assumed curve here, and then heat rejection. So that's our Otto cycle. So if I take a look at that on a TS diagram, we saw this before, we can calculate what the efficiency would be by comparing the network to the energy supplied. So the network would be what you get when you consider the change in properties from state 3 to state 4, or the enthalpy change. But if we assume constant specific heats, we can relate enthalpy to temperature. So T3 minus T4 is what we got back. The compression work was T2 minus T1, or the enthalpy change. And so the network is the difference between those two. And then the energy supplied was this Q in here is T3 minus T2. So when you work all of that out, you get this equation. You can relate the temperatures through the isentropic relations that I showed you before to the volume changes. And the volume changes are just expressed in terms of the compression ratio, R sub C. So when you're all done, you can calculate the efficiency for the ideal engine as 1 minus 1 divided by the compression ratio to the power gamma minus 1. Remember, gamma is the ratio of the specific heats. So for nitrogen or air, for diatomics, you can show that gamma is roughly 1.4 rather. However, when you add other species to the mixture, like you add some gasoline to the air, gamma is reduced. And in fact, you can see from these charts here that the efficiency versus compression ratio decreases significantly depending on the value of gamma. So this is something to remember when comparing different engine concepts, is depending on what you're compressing and so on, you can have quite different efficiencies. So the ideal efficiency of the Otto cycle, as shown in this equation, is a function of only two variables, compression ratio and the ratio of specific heats. I can increase the efficiency by increasing the compression ratio. Increasing gamma also is useful. This increases the pressure rise during combustion and increases work extraction during the expansion stroke. So both effects, increasing R sub C, compression ratio, and gamma, result in an increase in efficiency for my engine. Okay, that's what we learned from thermodynamics for our Otto cycle. But actual cycles differ from this. For example, the assumption of constant volume combustion is obviously not correct. Even with HCCI, very fast combustion, it's not necessarily isochoric or constant volume. We have a finite duration. So the duration of combustion is limited also by mechanical constraints. Even if you could have instantaneous combustion, high pressure rise rates and audible engine noise, high mechanical stresses would make that engine undesirable. The assumption of a calorically perfect fluid. In reality, the specific heats increase with increasing gas temperature, and this causes gamma to decrease. So you don't get the nice 1.4 efficiency that you see over here. Say for a 16 to 1, you'd get 70% efficiency. You don't get that, unfortunately. Also, we made the assumption of isentropic analysis here of adiabaticity. In other words, no heat losses. But in fact, we have large temperature gradients near the walls resulting in significant heat losses 20 to 30%. I'll show you results that show how much heat loss impacts combustion. Other assumptions in these engine system models that I showed you, these 0D and 1D models, we assumed that we had isentropic compressors, superchargers, turbines. We didn't use the exact maps from performance maps generally. Typically, we assume that the compressors and so on have efficiencies of 0.7, as we discussed last time. Variable geometry turbines, slightly less efficiencies are assumed to be 0.65. We also have charge coolers, like for example here's our compressor. We go through a charge cooler. Here's our intake manifold. We need to model those. They often assumed to have zero pressure drop, fixed effectiveness. Coolant temperatures are assumed. So a lot of assumptions go into these determining engine performance. Nevertheless, even with all these assumptions, you can still learn a lot about internal combustion engines. So I'm going to mention some analyses that show just what kinds of things you can learn. So starting from a zero-dimensional closed cycle analysis, we're going to represent combustion as energy addition to a closed system. So that's what's going on in the combustion chamber. Fuel injection or mass addition will be assumed to occur from a certain crank angle. It will be called the start of injection crank angle. And injection will occur for a certain duration. Pressure and mass would be integrated over the closed portion of the cycle with specified initial conditions at intake valve closure of the pressure, the temperature, and the composition of all the species in your residual and fresh gas in the combustion chamber. And then the post-combustion composition is typically determined assuming that you have complete combustion, which we also know is not necessarily true. Minor species such as CO and NO and so on are typically not considered during these simplified closed cycle analyses. So here are the equations that you'll see in those typical papers. They're all really based on first law of thermodynamics, which we've seen now several times, heat loss term, pressure, volume work term, and the rate of change of energy in the combustion chamber. So if I take a look at this equation here I have the change in pressure with crank angle. I can relate that to the combustion, rate of combustion, and the rate of heat loss. I need expressions for those, and we'll be talking about them in a minute. And here is my PDV work term, ratio of specific heats, volume of the combustion chamber, instantaneous volume. So combustion, how do I model combustion? I need this dQc dt, the rate of heat release with crank angle. At time I, I'm going to use what's called a Webby function, which is essentially a curve fit of experimental data on combustion rates in this case, spark ignition engines. It's an exponential. It has some parameters, the constants here, which are typical values around 2 or 3. Our start of combustion time needs to be specified. The duration of combustion going from 10% burn to 90% burn has to be specified. And so I can get the amount of fuel burned as a function of crank angle from such an empirical formula. I can then compare that at 2 different times and divide by the time interval to get the rate of heat release by multiplying by the lower heating value and the mass of fuel in the chamber. So that's this first term here. The second term is the heat transfer term. Well, here we use what's called the Rng Model. Here it looks like the Newton law of cooling again. We have the convective heat transfer coefficient multiplying the appropriate areas, for example, the piston area, the head area, the liner area. We need to know estimates of the temperature of the piston, temperature of the head, temperature of the liner. What do you mean, temperature of the liner? Well, you know it varies, right? You know the piston temperature varies, but you just pick some kind of average across the combustion chamber. Obviously, with CFD, we're going to do a lot better than that. But for these models, this is what's done. How do you get this heat transfer coefficient? Washney proposed this formula back in the 50s, I think, where basically he said the heat transfer coefficient depends on the bore of the engine. Again, some constants here. The intake pressure, the intake temperature, and then this quantity W, which depends on the piston, the volume, basically, and temperatures, pressures, and then the difference between the motoring pressure and the actual pressure. So somehow it's related to that gives you a feel for how much combustion has taken place. That influences this W. Also, the piston velocity appears here. So that goes into determining the convective heat transfer coefficient, which then gives you this guy. So we can then calculate the pressure change with crank angle using our first law analysis in response to the combustion and the heat losses. So it's kind of interesting just to see some of the other parameters. So for example, we need to know something about the pumping mean effective pressure. How much energy does it take to pump the fresh charge into the combustion chamber and then purge the combustion chamber? The friction mean effective pressure is, again, a measure of how much energy is required to overcome friction. And when you're all said and done, the parameter that's of most interest is the brake thermal efficiency. Brake thermal efficiency, you can show times the lower heating value, is the indicated mean effective pressure, the gross value, minus the pumping mean effective pressure, minus the friction mean effective pressure. So where do we get these from? Well, these we have to estimate from experimental data, the pumping mean effective pressure, the friction mean effective pressure. This one we can measure the indicated mean effective pressure by measuring the pressure trace and, as I showed you earlier, evaluating the mean effective pressure. The Department of Energy has a goal for heavy-duty trucks in the United States to reach 55% brake thermal efficiency. Most of the big players reached 50% in the last round that ended a year or so ago. And now the latest Supertruck 2 venture is to show that they can reach 55%. A lot of people are pretty worried about how they're going to get there. And this chart kind of shows why. So first thing to note is if you plot brake thermal efficiency versus the load, you see that in order to get high brake thermal efficiency, you have to be at high load. The other thing is that it depends on what the gross indicated efficiency is. So if you have a gross indicated efficiency of 55%, that's going to be an incredibly efficient engine. You'll be following this blue line here. You'll never reach 55% brake thermal efficiency. You have to have a combustion process that has a gross efficiency of 60% before, at a certain load of 15 bar here, you'll reach this DOE goal. And as you can see, if you were able to get even higher efficiencies, you would be able to see that type of efficiency at lower loads. But again, this is quite unlikely. I'm going to show you some results later where we have actually reached gross indicated efficiency close to 60%. And from those results, we think that, with the appropriate design, you could perhaps reach this 55% target, but we'll talk more about that later. Friction. Okay, this is another aspect here, assumed to be 1 bar in doing these calculations. Typically, in the models, you use what's called the Chen-Flynn model, which essentially says the friction mean effective pressure depends on the pressure in the combustion chamber, the maximum pressure in the combustion chamber, peak cylinder pressure, the engine speed, and a squared piston speed term. So friction goes up with the square of the speed of the engine. Okay, so I'm going to recommend, if anyone's really interested in this topic, that you read this paper in the International Journal of Engine Research by George Lavoie and others, where they basically assumed a particular engine. It's a light duty, like a typical gasoline engine, 90 millimeter to bore to 100 millimeter stroke. Compression ratio of 12, You see the intake valves here, intake valve opening times and so on, exhaust valves and their timing. So this was an engine that they took as their baseline engine. The operating conditions were engine speed was 2,400, piston speeds of 8 meters per second. You have to remember that piston speed is something that you don't have a lot of control over. Like in racing engines, maybe you can get as high as 20 meters per second. So this is a typical value. Equivalence ratio for the charge, they looked at a range, and we'll talk more about this later. Exhaust gas recirculation up to 80%. So that's keeping 80% of the previous cycle's charge in the combustion chamber. Exhaust pressure range, intake temperatures, shown here. Wall temperatures. Remember I mentioned how you have to guess at what the head, the piston, and the cylinder liner temperatures are? Well, here's their guesses. The turbocharger efficiency. Remember we said 70%? Well, here they're looking at a variety of different turbocharger efficiencies to see the effect on the results. The 10 to 90% burn was 25 crank angle, and the timing of combustion was, as shown here, 10 degrees after top dead center. The model that they used in this paper was the Washney for the heat transfer, the Weeby for combustion, Chen Flynn for friction. They actually even had a NOx model in this paper. You might recognize this equation. It's the one I showed you earlier. It's the turbocharger equation that relates the exhaust pressures to the boost pressures and the ratio of specific heats for the intake charge and so on. Here are all those efficiencies, the product of these. Remember, they've chosen as a range of efficiencies. The burn duration is, again, our Weeby number and our heat transfer through Washney. Here's the friction mean effective pressure equation that I showed you earlier as well. So here are some of their results, and these are very interesting. What they show is the gross efficiency of this particular 12-to-1 compression ratio engine. And let's focus first on the top set of plots here. Each one of them shows the efficiency as a function of crank angle around top dead center. So the line here is top dead center. And in this first one, they're assuming that, and in fact, this whole row, they're assuming that the engine is adiabatic, no heat losses at all. And they're assuming that the combustion is occurring with only a 2-degree combustion duration. So here's the cumulative heat release versus crank angle. Here's the 10% burn. Here's the 90% burn. Here's the 50% burn, it's called CA50. They're assuming that going from 10 to 90% burn happen in 2 crank angle degrees. And what you see is that when you do that, you get the highest efficiency of all of these because you're getting as close as you can to the Otto cycle efficiency. If you happen to have combustion occur after top dead center, the efficiency decreases because basically you started the expansion stroke before you release the energy and you've lost the opportunity to extract the work. Similarly, if you start before top dead center, you lose efficiency because you're basically fighting against the compression process. So the different plots you see here are for different 10 to 90 burns. If you have a 40 crank angle degree burn, that's a long time to get from 10 to 90, your total efficiency decreases because part of the combustion process is occurring very late and you're not extracting the maximum amount of burn. So that's interesting. Now, if you have the heat transfer turned on, you see the huge change. You're going from close to 54 whatever percent here down to 46%. So the heat transfer is really penalizing your efficiencies. Also, notice that the peak in these gross efficiency plots here occurs after top dead center. And that's because you have now a trade-off between heat loss and late expansion. If you expand too late, you again lose efficiency, but you've had less time for heat transfer. So essentially, there's a peak power point or a peak efficiency point after top dead center that is seen in real engines because they have heat transfer. The peak efficiency is not at top dead center like you see here with the adiabatic engine. So that's a very interesting set of results that makes a lot of sense based on the analysis tool described in that paper. They also look at other aspects that contribute to efficiency. So here again is our indicated efficiency, gross indicated efficiency. By the way, for this engine, the air standard efficiency is about 63%. And what we're plotting here is the equivalence ratio. So that means that if I have 0, I have only air in the combustion chamber, and my gamma is as high as it's going to get, right? It's 1.4 or whatever. But if I add some gasoline, the complicated gasoline molecule can absorb energy in a variety of different ways, which lowers the specific heat. And as a result, my gamma goes down, and I lose efficiency over here. All right, so the various aspects that contribute to the efficiency curve, let's just focus everything up to phi equals 1, which is stoichiometric. We have, if you compare these two curves, the solid and the dotted, that's for the 2-degree burn versus a 25-degree 10 to 90 burn duration. And you see we have an immediate loss of gross efficiency, gross indicated efficiency, due to the longer burn. This would be for the adiabatic engine, all right? And this is for the case with the longer burn. So we just saw those plots. Now, if we add heat loss, we just saw what happens there. Again, you see a decrease in efficiency associated with the heat loss. And the dependence on equivalence ratio is still there. The pumping loss, that's associated with getting the air into and out of the combustion chamber. And then the friction. So you add all these together, and basically this is what your brake efficiency looks like for this engine. It has a maximum value of about 36% indicated. So that's not net, right? No, I'm sorry, this is net because it has the pumping in it. This is net efficiency of about 36%. Okay, if I go beyond equivalence ratio 1, I have incomplete combustion. And so obviously I'm going to lose efficiency because I'm sending unburned fuel out the exhaust. So that explains those parts of the curves. What about dilution? So one approach, instead of having an equivalence ratio of 0.2, which by the way would be very hard to achieve combustion in because there's just not enough fuel to sustain a propagating flame. Instead of doing that, I can essentially dilute the charge with residual gas. So you can introduce what's called the fuel to charge equivalence ratio, which is the fuel amount, the amount of air and the amount of residual charge compared to the fuel-air ratio at stoichiometric. And so this is what the formula looks like. It's approximately 1 minus the residual gas fraction. So now if I go back to my plot and I go from phi of 0.2 to 1, I could either think of this as I'm just adding more fuel to air, and in that way changing the equivalence ratio from 0.2 to 1. Or I can think of keeping the equivalence ratio at 1 and change the amount of residual gas. And in his case, they went from 0 to 80%. So when they go to 80%, the equivalence ratio is still 1. But you have 80% of the charge is residual gas, already burnt combustion products. Okay, so now we can understand this plot. As I change phi prime, which is either EGR or equivalence ratio, you see the effect on temperature, on burn gas temperature. I've got much less heat release as I add 80% of residual gas, or if I only burn an equivalence ratio of 0.2. Gas temperature goes from about 2400 down to 1100, right? So exhaust gas recirculation is a powerful tool, you can see, for reducing the temperature of the combustion gases, and that way to reduce the amount of nitric oxide formed, for instance, which depends very strongly on temperature. But the other parameter that happens there is that you change the ratio of specific heats for the unburnt and the burnt gases. Now, the two curves that are shown here are the two ways of doing it. Either I add EGR or I reduce the amount of fuel. And so the solid line would be when I reduce the amount of fuel, I see an increase in the unburnt gas ratio of specific heats, as we discussed before, and a corresponding increase in the burnt gas specific heats. Okay, boost pressure. So remember that I mentioned earlier that in 1925, the turbocharger was invented, and this really shows what a great device that is, because by boosting the intake, you can reduce friction losses significantly. And why is that? Well, you're essentially sending high-pressure air into the combustion chamber, which pushes the piston down against atmospheric air in the crankcase. So you're getting some free work out of this system. Free, right? But you're getting some work out of the system, which effectively reduces friction. So if you look here at the actual engine with all of the losses that we discussed before, if I increase the boost pressure up to 3 bar instead of the normal atmospheric naturally aspirated 1 bar, I see a boost in my efficiency, my net efficiency, by a significant amount, as much as 10%. So this is very important from the standpoint of the overall engine system. You're not really changing the combustion that much. Your gross efficiencies are not changing as much. But what you are accounting for is the pumping and the friction becomes significantly improved. So this is a slide that that's in their paper that I think is particularly interesting, because now with all of their models, they can estimate brake efficiencies and compare them as a function of operating load. So down here is idle, over here is your maybe mid-load operating point. And looking at the theoretically, for this 12-to-1 compression ratio engine, the theoretically possible efficiencies from the system. Okay, so if I just take a look at the black curve here, this corresponds to just having air dilution. In other words, running with equivalence ratio of stoichiometric, and then reducing the fuel amount down to 0.3 of stoichiometric equivalence ratio. You can see that the effect of that is to reduce the brake efficiency, and you'll see our maximum is again around 38%. Now I could do the same thing, but keep the equivalence ratio equal to unity by adding exhaust gas diluent. And that gives me this blue curve here, very similar. And we saw the reason for that. The temperatures are basically very similar. The ratios of specific heats are not that different. So this is what explains this curve. The early intake valve closing is another way of changing the amount of charge in the combustion chamber. And then throttling is another way of doing it. These both have increased pumping losses, so you probably wouldn't want to follow those paths. But if you look at the combustion that's necessary to fill this space, SI engines will only operate over a certain range of equivalence ratios, because the flame speed basically peters out if the equivalence ratio is less than about 0.6 or thereabouts. So SI engines can operate in this range. HCCI engines, on the other hand, can only operate up to a certain equivalence ratio, beyond which the pressure rise becomes so intense that you can destroy the engine. You have homogeneous combustion everywhere in the combustion chamber. If you have too much fuel burning all at the same time, the pressure rise rate becomes unacceptable. So that's the range of those engines. And then in between are kind of hybrid engines, which in their paper they call advanced combustion engines, which could be blends of HCCI and flame propagation spark ignition engines. And so this is where they would be bounded. So this is just thermodynamic analysis using the empirical tools of the Washney and the Weber heat release curves and doing some optimization. Real engines are much more complicated. Okay, so we have intake flow, we have fuel injection, exhaust flow, we have spark ignition, or in diesel, self-ignition. We've got fluid mechanics to worry about, turbulence, wall heat transfer, crevice flows, the flow escaping past the pistons, spray dynamics, combustion, either premixed or diffusion, emission. So lots of things that we need to look at. And many of these things are sort of beyond being able to be handled with the simplified models that I've just discussed. So that's why 3D modeling has become so useful in this field. We have an unsteady, turbulent, two-phase reactive flow, which is about as complicated as you can get. I should have also said compressible up there. So just a little bit of history behind this. Actually, I came to America in 1972, just in time for the Arab oil crisis. And I remember standing online trying to get gas for my car here on the New Jersey Turnpike, because that was the only place you could buy gas. So anyway, when this happened, there were lines of cars, people waiting to get gas. And the government responded by saying, look, we've got these fantastic weapons labs that are using computers to solve weapons problems. Let's ask them to solve the problem of the internal combustion engine and thereby get by with much less fuel demand. So they went to the Los Alamos National Lab and said, give us your weapon codes, work with General Motors, Ford, Chrysler, and create the next engine. So my advisor, Professor Bracco, was one of the pioneers in this area. He worked with Los Alamos Lab people, and they converted their codes to engine application. There were people everywhere, many universities, including at the University of Wisconsin, who followed suit. And a whole bunch of codes were written primarily by the national labs to try to deal with the combustion process in an engine, all the way through till fairly recently. At a certain moment, people realized, hey, there's money in this. So let's make a commercial version of this. And Imperial College was one of the first that started out with commercial codes, the Star CD code, and then AVL, Fire, Ricardo Vectus, Fluent, and now Converge, Forte, and so on. So there are many commercial codes available. If you're interested, you can definitely pursue this. What I want to do, though, here is to talk about some of the submodels that are inside those codes. And that'll be the subject for tomorrow's lectures. But I want to say, if you are interested, there are user groups, there are sessions that you can go to learn more about engine CFD. So we spoke about volumetric efficiency. Well, you can calculate volumetric efficiency. Of course, there's always the issue of accuracy and so on, but this just gives an example of the kinds of things you can resolve with CFD. Here's that picture that I showed of the intake flow. These are streamlines. You want to make sure that these are nice and smooth and not separating from the flow passages so that you minimize losses in the flow. Here's the flow coming past the valves. And of course, you've got moving pistons, so the geometry is changing, and this sets up flow motions inside the combustion chamber. Those are very important because they actually affect the mixing of the fresh charge with the residual charge. And all of this can be calculated with CFD. So here, for instance, these pictures show residual gas distribution during the gas exchange in the plane of the valves at a certain moment during the intake process. Notice that the velocity vectors here show recirculation patterns associated with the flow separating from the edges of the valves that sets up these complicated flow fields. These flow fields, as I said, affect the combustion process as well. The equations are the same equations I showed you before, except now we have to solve them in 3D, not in 1D. So we have mass conservation, where we're looking at source terms on the right-hand side, perhaps due to spray, if we're adding mass because of vaporizing sprays. We have analogous equations for each of the chemical species. It might be one of the components of the fuel, or nitrogen, or oxygen, or NO, or whatever the species are that we're tracking. We have diffusion coefficients, and these are turbulent diffusion. I'll talk about that in a minute. We have mass from mass exchange during combustion that could generate or deplete a certain species. And then we also have from spray processes certain species that will be entering the gas phase from the liquid phase. So we have a multi-phase problem. We have the momentum equation. Here we have a source term due to the spray, which basically comes from momentum exchange between droplets and the gas. Gravity or acceleration forces, pressure forces, and then viscous forces, viscous stresses. And then the energy equation, like I showed you before. Here we have heat flux and species enthalpy diffusion terms. Combustion heat release, spray, source terms as the spray droplets vaporize, they steal energy from the gas. Pressure work terms, and then dissipation terms involving viscosity. So these are the equations. I'm not going to spend much time on them other than to say that these are what you'll find in the commercial codes and also in open source CFD code. For engines, most of the trouble comes from the fact that these valves are moving, the piston's moving, and so you have to have a mesh that is remeshing to correspond to the changes in geometry. And that makes it very difficult to solve with standard techniques. Turbulence is the other thing. Turbulence is essential, as we'll see when we talk about combustion. And that turbulence is generated through a variety of processes. For example, I showed you during the intake process, the flow past the valves generates swirling and tumbling flow structures that represent gradients in the mean flow, which then generate turbulence. We also have flow processes that occur by virtue of the change in the geometry due to the piston bowl, if you have a piston bowl. During the compression stroke, you'll have gases that are pushed from above the piston into the piston bowl, generating flow structures that in turn generate turbulence. And depending on the design of your piston, this can be quite different. Excuse me. We inject fuel into a combustion chamber. That injection can, again, lead to large gradients in velocity, which generate turbulence. These jets can impinge on surfaces and be redirected. Again, affects the entrainment, and the jet wall interaction generates turbulence. So turbulence is very important. Just one slide here about turbulence modeling. There's kind of two schools of thoughts, the Reynolds average Navier-Stokes approach and the large eddy simulation approach. Essentially what they're saying is, if I look at a point in the combustion chamber and I measure the velocity as a function of time in one coordinate direction, let's say ui, I'll get this fluctuating curve here. I can imagine an average velocity. That would be my capital U here. And then a fluctuating velocity, U prime. Generally, the U prime is a subgrid velocity. In other words, I have to model it because I'm not actually solving it. Whereas in the large eddy simulation case, I'm trying to resolve as much of this fluctuating component as I can. In the Rance case, I try to average it with a model called the K-Epsilon model. K is related to these fluctuations in velocity. It's the turbulence kinetic energy. The three components of velocity divided by 2, squared divided by 2. The length scale of the turbulence uses Taylor's hypothesis that says, okay, I know the mean velocity. If I have a time scale for the sort of rotation of one of these eddies that went past my measurement device, I can calculate a length scale of that eddy. And then the time scale itself, it allows me to calculate the turbulent dissipation rate, which is called epsilon. So that's the K-Epsilon model. So you'll see a lot of work being done in both the Rance and the LES type approach for modeling turbulence. I personally prefer the Rance approach because with LES, every run that you run is a new run because there's sampling that occurs. And so you never repeat the same flow field for each engine cycle that you run. Whereas with RANS, you are looking in some sense at an average of the flow. So in a way, it's easier to understand the results. But if you want to compare against an actual engine, single cycle engine experiment, even LES is difficult because although it's supposedly tracking each of these eddies and so on that corresponds to the fluctuations, you don't know whether that particular cycle corresponds to the one that you calculate. So it's very difficult. The RANS model is used throughout industry. Let me just leave it that way for now. Researchers obviously focus on the LES. So the K-Epsilon turbulence model is the most widely adopted of these two equation models. You have a transport equation for the turbulence kinetic energy. There's a production term, which is down here, I'll talk about in a second, dissipation, and then a diffusion-like term involving the turbulent viscosity and a parameter. And then you can even have turbulence kinetic energy generation by the spray, right? The droplets are decelerating in the flow, and they're giving up some of their kinetic energy to the flow, and that corresponds to this source term. And then the dissipation rate looks very similar, except it has several source terms. Again, you have your production term here, spray production, and so on. How do you get the production term? Well, you look at the mean flow strain rates. These are the gradients in the mean flow that then generate the turbulence. You can also think of them as generating Reynolds stresses, which correspond to those fluctuating components of velocity, and then use that to calculate the turbulence production rates. So this is basically the most popular class of models. And then the Rng model is a renormalization group closure model, which essentially applies to the epsilon equation, the dissipation rate equation, and gives you more insight into the parameters involved. So for example, a new term is added to the epsilon equation, which essentially is driven by the ratio of the flow timescales and the turbulence timescale. So you can imagine a case where the flow timescales are much larger than the turbulent timescales. That appears then as its influence on this parameter R, which then decreases the rate of turbulent dissipation rate change. So that's a modeling improvement that allows you to essentially account for variable strain rates in a turbulent flow. Another very important term is embodied in this term here, which involves the divergence of the velocity field. So in an incompressible flow, the divergence of the velocity field is 0. But an engine flow is compressible. And in fact, during compression, this term is positive, and during expansion, it's negative. So there's a sign change. And what we've found over the years is that that constant there has to change sign and magnitude corresponding to this change in compression versus expansion. So there's a lot of work written, a lot of papers written on the correct selection of these constants, C1, C2, and C3. And in fact, more recent work that we've done with Sandia National Lab is to try to what we've called the generalized Rng K-Epsilon model, where the constants in the model, these C1, C2, C3, depend on the nature of the stresses in the flow. So for example, if the flow is primarily unidirectional, which you can get by looking at the strain rate components in the 1, 2, and 3 directions, the Cartesian directions, then you'll have a certain value of this parameter n, which you then put into this equation, which then gives you a parameter, a value for the constant C2. And if you remember from this equation, C2 is the term multiplying epsilon here. If the flow is more planar or two-dimensional, you'll have a different value of n, and if it's isotropic 3D, you have a different value. So where do we get these from? We get this from DNS studies, fundamental studies of turbulence for unidirectional, radial, and spherical flows give you the values to be used for these constants that determine the rate of change of dissipation rate. So there's a lot of modeling that goes on here, and let me just suffice it to say that turbulence is still an area of active research. However, the models that are available do a fairly good job, as I think you'll see. So just to give you an example of that, here's some calculations by Federico Perini of the engine that we've been working with Sandia National Lab on. It has these two huge settling tanks, one for the exhaust and one for the intake. Here's the intake manifold, here's the engine itself, and so he has the entire domain discretized and in a CFD code. The engine is a 16:1 compression ratio. Here's all the details of the engine speed, 1500 RPM, and so on, the charge. There's no combustion here. This is just cold flow. This is what the port layout looks like. We have exhaust and inlet ports. And here's some of the solution details for spatial accuracy, time step accuracy, and so on. So it's a moderately boosted, low load operating condition. And we had, fortunately from Sandia, experimental particle image velocimetry measurements inside the combustion chamber that we could compare with the simulation results. And that's what this chart shows. Now, it's kind of hard to see, but let me just briefly show you. So the circle you see here is the bore of the engine. And we're looking at the tangential velocity component and the radial velocity component. You can just sort of see the valves in the background in this picture. The colors correspond to the experimental PIV is in blue. The standard K-Epsilon model is in red, all right? And these are profiles measured at 3 cross-sectional stations, which correspond to different times during the process here, from 240 crank angle to 10 to 180. And the green is the standard Rng model, and the other one, the black, is the GRNG, the generalized Rng. And as you can see, if you're comparing against the experimental data, there's fairly good agreement. Here, there's not quite as good agreement, but the agreement is pretty good with all of the models. But if you look at them overall, the conclusion is that the Rng models are better during the late intake. They capture some of the swirl profile information better than the standard models. And it's this type of thing that helps you to develop these turbulence models. This kind of experimental data is extremely rare. I mean, think about it. Making particle image velocimetry measurements in an operating engine. The engine itself is made out of quartz or glass, and a huge amount of data processing to generate this type of data. Okay, so to finish up today, what I've tried to do is to talk about, from very first basics, what goes into engine system models, and they can be used to provide estimates of engine efficiency, but there's some assumptions you have to make. For example, they have nothing really to say about combustion. You have to assume the timing and the duration of the combustion. You have to assume something about heat transfer losses. So all of these are assumptions, and basically you rely on experimental data to help deal with those assumptions. Multidimensional models are available, and they have actually been shown to do fairly well at predicting the flow. Combustion we'll talk about in the next lectures. But basically, if you're not able to calculate the flow, you're not going to do the combustion. So it's good news that you're able to look at flow structures. The 3D models require accurate turbulence modeling. And again, this is an area of active research. Very important in this is the use of DNS, because there are not that many other ways that you can generate the type of data needed to validate these turbulence models. And references for this section. So, I'm a little early. Questions, yeah. Yeah, so so the experimental PIV, let's just take one of these cases here. This one, for instance. At this location, which is kind of along the diametral plane in the engine, you see flow going down on this side. The velocity, these are velocity measurements, right? Tangential velocity. Flow going down on this side of the engine and flow going up on that side. So that's a swirling flow. And you see the models and the experiment do reasonably well, right? They pick up that swirling flow. The magnitudes are perhaps debatable, but at least you're getting those magnitudes. You're even getting the 0 point, which is the center of the swirl, which is pretty important, but the swirl precesses around in the combustion chamber. And this, by the way, is all at one height, 10 millimeters below the head. We have comparisons also at different locations, but this is just a sample of that data. If you go out to another diameter or another cross-section further down off the center diameter, you'll see here the flow field is quite complicated. You don't really see that same swirling flow. And none of the models really capture this extremely well. This crank angle at that location. But if you go a little bit later, you see that actually all of the models do quite well, with the exception of this red one here, which is the standard K-Epsilon model. But the Rng models and the Rng models do quite well. And they capture the details of the flow field measurement. Over here, you're still pretty early. This is on the exhaust side of the engine, this is the intake side. You had a flow coming through the intake and it's creating a mess inside the combustion chamber. You can see the experimental measurement here. It's really messy. The simulation results are quite far from the experiment. But later on, everything kind of approaches the experiment. So, I'm not sure that one could do any better than this. If you look at the radial velocity components, you can see there's significant differences between the experiments and the predictions. Some of this is also in the accuracy of experiments. But this is the best that I know of.
What happened with the third dimension?
Right, so that's, there are various planes, and each of these is a PIV measurement in one plane, but we have in the calculation that information.
Yeah, that compared as well.
Yeah. And that's what you would show when you're looking at tumble flows and so on. I just picked one example on this paper that Frederick has said, but there's a lot of other work as well.
Was this a high excited or?
No, this is just motor. Yeah. Simplest possible flow. And it's also influenced, depending on where you are, by the piston geometry, like. At early times here, the piston has a big influence because the flow is coming in while the piston is still near target center, being redirected by the piston. So you see a mess inside the combustion chamber in terms of velocity. And these are average velocities as well, remember that. Any other questions?
Is there a difference in the spatial resolution from the measurements compared to like a mesh in the model?
Very good question. So mesh resolution is one of the, there's this road over here that you sweep things on. And it's one of those things that people don't like to talk about, but we have tried our very best to use as accurate meshing and numerical method as we can. For example, we use body fluid coordinates, so we can track the flows are always going to be parallel to the boundaries. And the mesh resolution, we try different meshes. Don't remember that, we're talking million mesh cells here, million cell meshes. So these are several days of CFD simulation. And if someone says, well, double the mesh size, well, you have to multiply that by 8. So that becomes several weeks. So meshing is a big problem.
So as you noted, these are averaged results. Certainly on the prediction, I could do a cycle-by-cycle. So I would know what the uncertainty is relative to the average. I'm just kind of curious what that number turns out.
Very good question. When we do these simulations, and I'm not sure whether these ones did that, we actually run several cycles before the system kind of uniformizes and you get a constant result. Because the first cycle, the charge is moving, maybe the swirl is counterclockwise, and then after your first calculation, the swirl changes to clockwise, and then for the next cycle, it's the correct orientation. So yeah, you have to do 3 or 4 engine cycles before you calculate it. It's very good.
But if I did in the prediction, 100 cycles, would that average differ much
From 3
on the
cycles?
individual cycle prediction?
No, not with Prince.
So that is actually converging to an average value,
Yeah.
whereas the experiment probably isn't.
Well, they typically run, like to get a full field PID experiment takes many engine cycles.
Right.
Now the
statistics.
LES models, you could run many engine cycles and no two would be the same. But eventually you'll also get an average that looks repeatable. And there are questions on how to do that. So a lot of research. Yeah.
Do you think DNS will ever play a role in measuring?
Yeah, thanks for that question. One of our researchers, Mario Trujillo, is doing DNS simulations of sprays, and I'll talk about that also tomorrow. But anyway, his mesh size is, I think he was bragging the other day, 2 micron mesh. Yeah, we're talking 2 millimeters is a lot, right? So that's 3 orders of magnitude different, cubed. So if these take a day, these would be, 10 to the 9 times more. So it's not going to happen. But, sometimes you have to consider that type of resolution if you want, for your specific problem, to answer some questions.
But as he pointed out, DNS is playing a big role in terms of verifying certain submodels.
Absolutely.
So there's no question that it's extremely important. It's just that you're not going to do a systems calculation.
Just like, the guy at General Motors who uses these one-dimensional codes is not going to do a CFD calculation because he'll never be able to design an engine even with 2-3 day turnaround for each case. And if you're talking half a month or a month turnaround, he's not interested. Any other questions?
We talked about great thermal efficiency goals. Is that something that the DOE regulates?
The 55% thermal efficiency is the DOE's target. They came up with that target because they considered fuel consumption, CO2 regulations, all these factors, and that's how they have expressed it to the industry. They want a 55% correct thermal efficiency. Now you have to remember that before the challenge to the industry, the brake thermal efficiency was in the 40s, maybe 42%. So they've made tremendous strides. They've got up to 50% already. And the last step, the next step is 55, and maybe one day they'll go higher. For fuel economy, which is CO2, So it's all good. There's more to it than the engine as well. The trucking industry has streamlined the trucks. I don't know if you've driven behind one of them on the highway that have those tail flaps at the back, that prevents the low pressure regions at the tail of the vehicle from increasing the drag. A lot of aerodynamic improvements, and now there's even logistics where you can use your GPS to figure out if there's a hill coming up and are you going to speed up or you're going to turn off the engine and coast down the other side. I mean, many things that you can do to improve fuel efficiency that have nothing to do with the engine, but have to do with the vehicle itself. All of that goes into the DOE's thinking. Okay, let's meet tomorrow afternoon. Sorry.